Hello, good morning. My name is Carlo Giuffoni. I work at the University of Venice, and I coordinate the research program on climate change adaptation at the Fondazione Enrico Mattei. So I'm very glad today to introduce this webinar, which is the first of a series of at least 4 that we are organizing for the coming weeks and coming months. As you can see from this slide, the general topic and the general title of this series is Open Issues and Future Perspectives, and this is the first episode. So I think it's a very good idea to start with Pietro Teatini. This is, again, a collaboration, so a co-organization, as you can see, between Fondazione Enrico Mattei and University of Venice, and these 2 programs, so the Adapt Venice and the Waterlands program, new project, sorry. So it is indeed a convergence of interest, I would say, on this idea of contrasting sea level rise in Venice by seawater injections below its lagoon. Pietro Teatini is a very well-known colleague from the University of Padova, where he teaches hydrology and hydraulic engineering, and he has several roles in international organizations as UNESCO chair and so on. All these roles are more or less related to geology and aquifers, so water and geology, I would say. And I'm sorry, Pietro, if I'm too simplistic in describing your competencies. Anyway, also just to conclude my very quick introduction, one of the reasons why we were contacting Pietro in recent time is that I've recently written a book about Venezia e cambiamenti climatici, so Venice and climate change. I published that book last year, and when I had interviews with journalists, they were always asking me about my project for uplifting the city of Venice, and every time I was repeating, well, that's an interesting project, but it's not of mine. I mean, it's Pietro Teatini and colleagues that proposed this, and I cited, of course, your book, Pietro. So with that, I will really end my short introduction. Just remember all the participants that they can raise questions to Pietro by using the chat, and I will then report on your questions after Pietro's presentation. So Pietro, once again, thank you for being here, and the floor is yours.
Thank you so much, Carlo. So let me share. Okay, so I hope that you can see my screen now. So yeah, I'm Pietro Teatini. Thanks. I work at the University of Padova in the Department of Civil, Environmental and Architectural Engineering. And yeah, so the title of this talk is how we can contrast the relative sea level rise in Venice by seawater injection below its lagoon. And it's I would say novel idea in the sense that it's peculiar. I would say we developed peculiarly for the city of Venice, and we will see how and why. So let's start from something that it is well known to everyone, and at least to the people that live in Venice and to the people that make their activities in Venice. So the city of Venice has really has been affected, and it is also affected nowadays, by relative sea level rise. What does this mean? It means that the city of Venice has lost elevation with respect to the mean sea level over the last decades. And here we have some picture that show why this happened. It happens due to at least two factors. What we call it land subsidence. So Venice has lost really elevation with respect to the mean sea level. And this has been caused by two causes. One is the so-called natural subsidence, so natural consolidation of the quaternary system that compose the pop plane. And we cannot do anything about this. This is really natural process. And the other one is induced land subsidence. So land subsidence caused by groundwater pumping that occur, everyone know, occur mainly until the 70s in the mainland, and of course as with effect also in the city, on the city itself. And then we also have, of course, the other component, the component related to the sea level rise. Sea level rise that, let's say, occurred with a rate of about 1 millimeter per year if we move back to the past century. But this sea rise is already increasing up to more than 1 millimeter per year. We can see at least a couple of millimeters per year nowadays. And unfortunately, it is expected to increase much more over the last decades and over the last part of these centuries, with the different behavior, as this picture on the top show, depending on different scenarios that IPCC has done. But anyway, independently on the scenarios, it is nowadays very clear that the city in few decades will lose several centimeters with respect to the mean sea level, and which is the effect of this. Let me see. Okay. The effect is, of course, what the city has experienced until, let's say, 2020. So a really increase of the frequency of the high level, high water, what we call the number of acque alte. So, and these are graphs that are really, let's say, published in several publications by a lot of people. And we can clearly see how the number of acqua alta event really increase, I would say, exponentially, if we look at the tide gauge that we have until the 1870s. So the issue is, okay, how we can manage this huge problem. We want to keep Venice, let's say, more or less in the situation as it is. So to maintain the city, the people that live there, the activities, and of course the cultural heritage as it is. So the solution that it has been proposed, as everyone knows, is the MoSE project. So these mobile gates that are located at the 3 inlets of the lagoon, and when high tide, so a tide higher than 110 centimeters above the mean sea level is expected to occur, these gates are risen, and therefore this way they are able to disconnect the water level into the lagoon from that outside of the lagoon. And so to keep this difference in the water elevation, and keeping, therefore, Venice, I would say, dry without significant floods. And the MoSE project, we know that the construction started in 2004, and the completion should be planned. It was planned at the beginning in 2014, but then it was postponed to 2019 and now to 2014. So nowadays we know that it's still in operation. We have already saw its effect and its effectiveness in keeping dry the city, but we know also that it is not really completed yet, and therefore, due to this, for example, any closure and opening nowadays it is really expensive due to this reason, because it's not really completed. But over the last 2-3 years, so when MoSE was start to keep safe Venice, it has been observed that it has some negative effect for the health of the lagoon and its morphological landforms. there are a number of colleagues, again, from my department or in my university that has clearly shown, for example, that when MoSE start to become in operation, the sedimentation rate over the marshes, or what we call it generally barene, is significantly decreased. But this sedimentation is really fundamental in order to keep the marshland more or less at a constant difference with respect to the mean sea level. So MoSE keep safe Venice, but it does not it has some drawback with respect to the natural marshes. So we have to, it is clear that at least to the scientific community, that we have to plan with some additional solution. Otherwise, in a few decades, MoSE will be need to be closed so frequently that for the lagoon itself should be really a big problem. So which kind of solution we can put in place in order to complement the activities of the MoSE? And what it is really important is that this solution must be ready, I would say, in a short to medium term. So not really at the end of the century. We cannot wait decades and decades to start doing something, because then it will be too late. So this was the starting point. And so what we did, we start observing what we can see in other part of other region of the world, and taking this or taking advantages of satellite monitoring systems that are nowadays available, we can clearly see that there are several places all over the world where the land surface is not subsiding as occurred in Venice during the 70s, but it is uplifting. So it is moved upwards. So these areas gain elevation with respect to for example, the surrounding sea. And this is due to the fact that people inject fluids into the subsurface. So if we remove fluid, we cause compaction of the deep layers, and therefore loss of elevation of the land surface, the phenomenon that we call land subsidence. But we can clearly reverse the process. So if we inject fluid, it has been observed in several cases all over the world that the land surface move upward, even though we inject at a very large depth. So pressure is really able to expand the deep layer, and therefore to make the land surface to move to upward. So based on this observation, we had the idea, and we tried to understand, okay, so if this happened all over the world, in several places all over the world, why don't think to do something similar for Venice? And see if we inject water into the Venice subsurface, how much we will be able to uplift the city. I have to make a premise that really in the past decades, myself, but also the professor with which I worked, that it was Professor Gambolati, we really work a lot on land subsidence in this area. So the first land subsidence model of the city of Venice was done by Professor Gambolati. And so we are really familiar with this environment and the subsurface of the city. So there are really a lot of information that we have acquired over our research during the last, I would say, 50 years. And so the idea is, okay, let's try to use all the information that we have and to make a computation and see how much we can expect the city would be, let's say, rising with respect to the surrounding lagoon water, injecting fluid, so water. We have a lot of water. The lagoon is really full of seawater. So the idea is to inject the seawater into deep layer. Deep layer for two reasons. First of all, because we want to use saline water that it is, I would say, freely available. So not use fresh water that it is nowadays really a very precious resources. And if we use seawater and we go at larger depth, below 500 meters, there we have saline aquifer. So the water in the deep aquifer, the aquifer below 500 meters, more or less, already contain salty water. So we use seawater and we inject this seawater in salty aquifers. So what we made together with the CNR also in Venice, we acquired with a number of different projects. We acquired all the available information that was, let's say, acquired during the last, I would say, 50 years in the Venice area. So we have boreholes, and this is the map on the left. You can see some red dots that represent deep boreholes. We have several geoseismic acquisitions, so geophysical acquisition that was done in the 60s and in the 70s, and you can see those green lines. So they represent really lines section over which we have a very good knowledge of the subsurface. We also made new acquisition, the blue line that we did in the offshore Adriatic, in order, let's say, to have a more uniform and more coherent as possible characterization of the structure of the aquifer system below Venice and below the lagoon itself. So we built up what we call it a three-dimensional geological model below the lagoon based on this kind of information. And then this geological model is being used to build up a finite element model. A finite element model means a model over which we are able to solve the equations that govern how the flow moves in an aquifer system and how this aquifer system responds in terms of displacement, in terms of deformation. And okay, so what then we say? Okay, we know and we have reconstruct quite carefully, let's say, and in a very detailed way, the subsurface of the lagoon. And now let's try to make this sort, if you want, of exercise, so or hypothesis or scenarios. Let's put 12 wells on a circle centered in Venice, specifically if you want a center in Rialto Bridge. And this circle has a diameter of 10 kilometers, and we inject through these wells, we inject the lagoon water into this deep sandy layer. And let's keep this injection, the scenarios that we did is to continuous injecting for 10 years, keeping or controlling properly the maximum overpressure at which this well will be injected in the aquifer. This is a key parameter, so what it is technically called overpressure value, and this number was fixed at 20 bar. This is, of course, it changed from place to place, from basin to basin, and also from depth to depth. But for that specific target, and below the Venice Lagoon, this 20 bar allow us to be sure that we will not cause any cracks, any fracture into the subsurface system. So we don't want to generate any fissure or cracks. And to do this, we have to keep the pressure, the overpressure below this bound. So we cannot inject very quick. We have to inject in a proper way in order to match this constraint that we have. We have 12 wells, and these two pictures on the bottom show, okay, how, let's say, the pressure will, let's say, will behave, and how the discharge, so how much water we will inject into the different, into the various 12 wells. And you can see that there are different behaviors, so with different values. And this is due to the fact that we, as the geological setting is not uniform, there are some complexity. We try with different pumping rate to generate an uplift, so a displacement of the lagoon and of the city of Venice itself, as more uniform as possible. Okay, uniformity, of course, of the displacement is another important issue that we have to guarantee. We don't want to generate any instabilities in buildings, bridges, and churches. So playing carefully with the discharge rate, we are able really to succeed in this requirement. So now I'll show you some results of the model. Okay, the first one, in this slide, I'll show you how the pressure or the overpressure will change, for example, into 3 of these aquifer systems. So there are several sandy layer into which we inject the water. And just to show you some example, you can see with the different colors, you have the color bar on the right. So blue means that there is no effect. We do not have any pressure rise. And when we move from blue to green, yellow, and red, this means that the pressure in the aquifer system increased due to the fact that we inject the seawater. So this is the situation after 1 year, after 2 years, 3, 5, and you can see that, of course, over time, the area where the pore pressure increase, it becomes larger and larger, and the value also becomes higher and higher. And this is the last at the end of the 10 years. Okay, so we will have an area, of course, centered in Venice, where the wells are located, where the pore pressure is increased. If we move far away to the north and to the east or southeast, of course, at a certain distance, there will be no effect at all. So then, what is the effect of this pressure increase in terms of displacement of the lagoon bottom and consequently of Venice itself? This is the results that I can show in this other slide. So this slide show the uplift, so the movement, the gain of elevation of the lagoon bottom in centimeter. Okay, so in this is 2 centimeter. After 3 months, the area centered of Venice will gain 2 centimeter with respect to the present elevation. This is after 6 months, 1 year, 2 years, 5 years, and 10 years at the end of the simulation period that we have considered in these studies. So what we can observe? We can observe that, of course, the central part where Venice is located uplifted more than the surrounding part. We can observe that the amount is on the order of 26 centimeter. We can say between 25 and 30 centimeter. This is the maximum value that occur in Venice itself. And we can observe that also that the uplift is very uniform. So the city of Venice will be uniformly risen by this amount without more or less any differential displacement. And which is the effect of this? So 25 centimeter. Okay, if we suppose to have a city of Venice 25 centimeter higher, what does this mean in relation to the high tides or to the aqua alta that generally, let's say, affect the city? We have made a couple of, let's say, simple analysis. First of all, looking back to the past. So if we go and see back what happens to Venice, and this is what this graph show, okay, we can see that, let's say, over the past century, globally, the city of Venice has lost about 24 centimeter with respect to the mean sea level, the mean level of the Adriatic Sea. With 25 centimeter higher, it means that we could be able to bring back the city to the situation at the beginning of the 90s. So in some way offsetting completely the loss of ground elevation with respect to the mean sea level that has been occurred since, let's say, those years up to the present time. If we look at the future, what happens in what should we expect? in terms of, if we look in front of us, this graph show, let's say, a curve. It's a bit difficult, a little bit more complex to understand, but it's analysis that show the frequency, so the number of events that of aqua alta that we have with respect to the height of the tide. So and this is data that has been obtained by processing the tide gauge records at Punta della Salute. So if we look, let's say, with what happens with a mean sea level that should be 50 centimeters higher than now, than the present condition, this means that we should expect to have more or less 250 events per year higher than 110 centimeters. So it means that more or less the MoSE should be close, I would say, almost every day or extremely frequently. Okay. What happens if we have a city that it is 25 centimeters higher? It means that the need to close the MoSE will reduce significantly, based also on this kind of analysis that, if you want, is quite simple, but it gives an order of magnitude, a reliable order of magnitude. It means that as a city 25 centimeters higher would require only 30 events, 30 times the closure of the MoSE per year. That is really much less than the 250 events. So really, we can say that this project of uplifting the city, in some way, we can also in some way say that we will save the Venice, the MoSE efficiency in keep the city dry without experiencing flooding, but simultaneously this has, of course, a very positive effect for the natural environment. So we do not need, it will not be needed really also in the future to close MoSE so frequently, with a positive feedback for the natural environment. We make some analysis also in terms of differential displacement, because so this is, I would say, as you see from the picture, that the uplift will be very uniform, but there are several people or colleagues of us that are a bit worried by our let's say proposal, and because they say no, you will anyway create or generate with this idea differential displacement that will collapse the city, or part of, will damage, let's say, with the potentiality of damaging the buildings of the city itself. And so what we did is really make a detailed analysis, a quantitative, I would say, analysis, not just a matter of let's say thinking or warning, but we went and made computation, and we compare, and this is the picture that we have on the top left, the so-called differential displacement. Okay, so how much there will be differences in the displacement of points in the city that are close one to each other. So what will be this differential displacement due to the uplift with respect to the differential displacement that the city has already experienced? And these are the two pictures that we have on the bottom. The one on the right hand side, you can see a map of Venice. The bottom right picture, it's a map of Venice with the color that represent the differential displacement that the city has already experienced due to land subsidence. Okay, so when the city during the 50s and the 60s. And we can see that there are part of this city when we have the dark color, or the dark red or the blue color, where we have value that are really in the order of 10 to the power of minus 5, 10 to the powers of minus 4. These numbers, if we compare this number with the one that we let's say caused by uplifting, we can see that these values that the cities has experienced in the 60s is already much larger. So then those we will it will be caused by the injection of seawater into the subsurface. And we can also say that nowadays there will be even much larger differential displacement caused by building restoration. And this is, for example, the two figures that you can see here on the top left picture. These are displacement that has been detected by satellite measurements. And you can see that there are points with different colors. This point represent position for which we can monitor accurately the displacement using satellites. We have points colored by red, where that means huge displacement. We have points colored by yellow, that means, or green, very small displacement. And therefore we can compute which is the differential displacement that this part of the city, that it is really on the back of the San Marco Basilica, has already experienced. And also in this case, we have that these differential displacement are more than 10 times, so we can say 20 times larger than those that the uplift will cause. So from this point of view, we can say that we are pretty sure that this intervention will not cause any damages to the city itself, because the city is already experienced differential displacement much larger than those that could be caused by seawater injection. We have also tried to make some analysis in respect to which could happen to not only the city, but also, let's say, to the surrounding lagoon. And we will see that there will be, of course, the central part of the lagoon that will gain some elevation. So the bathymetry will reduce a bit in the lagoon close in the surrounding of Venice, and also in the marshes. So there will be some positive effect also on the natural marshes in the surrounding of the lagoon, that will gain some elevation with respect to the mean sea level, and also on some artificial marshes. And so this is, for example, match very well the objectives that other studies that we are carried out within the Vital project together with We Are Here Venice, that is strictly related to the resilience of these natural and artificial marshes with respect to relative sea level rise. So nowadays, one big problem for the marshes is to be able to maintain elevation with respect to a sea level that it is rising. And therefore, this let's say, pumping seawater below the lagoon bottom will also affect positively the marshes surrounding Venice with respect in this let's say, in this sense. I will close with this final couple of slides. So before, the idea is, okay, can we start directly playing with the full experiment, so with the full test of uplifting Venice? We also say probably no. So it should be much better to try to put in place what we call a pilot project. So the idea should be, okay, let's do a smaller project in an area far from the city, not too far, so stay within the lagoon, so the environment is the same, the geology is exactly the same, but we move a little bit far from the city itself, and let's try to inject, for example, some seawater in the same deep aquifers, but only through 3 wells. And we put a lot of other instrumentation in the surrounding in order to monitor what will be happening in terms of elevation, in terms of expansion of the deep formation, in terms of pressure distribution. So in order to keep really under control all the parameters that, of course, that they are affected by some uncertainty. So the idea is really first to put this in place, try and based on that, test really the feasibility of the full project. Also, in this case, we make some preliminary modeling analysis with the idea of inject through these 3 wells for 2 to 3 years. So a shorter project is not needed to go for 10 years, but we can keep shorter and with a smaller injection rate too, and check which kind of displacement we will be able to have. And this will really make a sort of proof in order then to decide if to move toward the full project or to take a different decision. So what about the pilot project? We are trying to, let's say, to push as much as possible, as much as we can, this idea, and we have started, let's say, trying to figure out how this project could be managed. So our idea is to put in to establish a sort of core team made by scientists and researcher working at the University of Padua, CNR, we are here Venice, and also some external experts, with the main goal of developing the executive planning of the pilot project, to manage the project itself, and of course to analyze the experimental outcome. Then there will be also a sort of international panels, as what we generally call scientific advisory board, made by scientists, well-known and scientists in the field, different fields, for example, lagoon hydrodynamics, geomorphology, geomechanics, also economics or legal expert too, in order, let's say, to fully supervise the pilot project for the scientific and economic and administrative point of view. The pilot project should be consist of 3 main phases. A first phase that should be related to the inception and site scoping. A second phase related to drilling of the first exploratory boreholes and trying to acquiring information from a first borehole. And then the last and third phase should be related to the drilling of the other boreholes and put in operation the injection, of course, and controlling and checking which will be the results. The table on the left-hand side is so how this, let's say, pilot project should be, let's say, should be developed over time. The idea should be that in about 5 years we will be able to reach the end and to have a final, let's say, a final result, a final setup that give us the possibility to really decide in a scientific based way to move toward the full project or not. We have also tried to make a first preliminary analysis of how much this pilot project would cost, and the total budget, as you can see from the table, this is a rough estimate already, but let's say in some way reliable, is around 40 million euros. That means 8 million euros per year, as the project will last five years. So 8 millions is an amount that it could seem quite huge or large, but we have to consider that we are speaking about the safety of Venice. So probably I would say not so large compared with the other investments that are currently carried out in Venice itself, its lagoon, but also in Italy, just speaking in Italy. So to conclude this talk, so we know that the city of Venice is threatening by the sea level that it is rising. We have MoSE that is start working to become in operation, but it is clear that MoSE alone cannot work for long. It must be complemented as soon as possible by other strategies, and so we say action are really urgent now. We propose this idea to inject seawater into deep aquifers, and this can give us the possibility to rise the city by 25-30 centimeters. If you want, this is not, of course, cannot be viewed as the final project to maintain Venice safe forever. No, it's not this. If you want, it is also a temporary intervention, but it is an intervention that will give us the possibility to have at least 40-50 years in front of us, where the city and the lagoon will be maintained more or less in the same condition, and then we will have more decades and more time to think to some different permanent solution that possibly the technology that will be developed in the next decades will be the possibility to play with. This idea of seawater injection has been really received a lot of support from many famous scientists in the field of hydro-geo-mechanical science. This is some list of people that send us really letter of recognize about this idea. And this idea is not new, so it's not something that we developed recently, but it is, I would say, announced 15 to 20 years ago. And at that time, in some way, it was put on aside as, let's say, the policymakers has at the end to prioritize MoSE intervention. So now MoSE is there. I think that it's really time to start thinking something different. So our first step should be develop this pilot project. Pilot project should be, I would say, put in place and realized in a relatively short time frame. We say 4 or 5 years, and this will be very useful to check for the technical feasibility of the uplift of the full city, to anyway build up new science, understanding of the subsurface of the Venice Lagoon, and also therefore to validate, let's say, the safety of this procedure. So anyway, it should be important in, or provide, it should be important in at the end, also independently on the result that it will get. And finally, just to say that this sort of intervention, so fluid injection, will require standard equipment. As I show you at the beginning, there are already a lot of places all over the world where fluid is injected. So nothing new has been to be developed for that from this point of view. And we can also say that, let's say, the funding is relatively modest with respect to other intervention and budget. And I'll close with this. Of course, I have to thank all the co-authors that it's a work made by a big group of people that has worked on these topics. And if we have more interest on that, we published this book that also Carlo nominated at the beginning of this talk, where we summarize a bit in a non-technical, not strictly technical way, this idea and this project and the result too. So thank you.
Thank you very much, Pietro. It was indeed quite stimulating, as expected, I would say. But having read your book and but listening to your presentation was indeed quite stimulating again, and also I could see how your proposal is in fact very detailed and concrete in a sense. So I think we can start with the questions. We have a question from the audience, and we have also other questions coming, and I do have a list of questions myself. The first that I will take from the chat is says, in regards to the stress of the buildings, the existing data is based on the effect of sinking elevation rather than rising. And it is also based on structural integrity of buildings 60 to 70 years ago. How do the current projections adapt to these differences?
Okay, so let's say, what the city is experiencing now in terms of differential displacement in relation to elevation or land subsidence. It's something that, let's say, in terms of absolute value, it was and it is really much larger nowadays, because every time activities are done in Venice, for example, cleaning the canals or restoring some buildings, we can clearly observe through SAR interferometry that the surrounding of the area where the works are located are affected, the buildings are affected by differential displacement. And this differential displacement that can be really quantified through these SAR measurements are up at least one order of magnitude larger than the one that we will get due to, or we compute, let's say, with our model due to seawater injection. So let's say this I would say that this is not really a problem, in the sense that it is not what happens to the city in the 60s and then everything was frozen. The city of Venice is really, I would say, the buildings are living buildings. They continuously move and adapt to the different intervention and activities that the Venetians do continuously. And we never, let's say, read about building or churches that crash down. So it seems we do not feel this as really a true problem associated with our ideas.
Thank you. So continuing on this in this direction, we say, okay, the buildings are probably more affected these days by these phenomena that you mentioned, than what could be the impact of these future projects. But do you see other risks? I mean, if I'm not mistaken, for example, this system is made of wells and pumps. These wells and pumps should stay in operation also beyond the 10 years, right? So to maintain this kind of pressure below the city.
Yeah.
What are the risks that you envisage here?
Yeah, that's a good point. I would say better than the first one, more reasonable concern, in the sense that, yeah, so injection will need to be continuous. So it will need to be continuous with a much smaller rate. So the pumping rate, once, let's say, we will have acquired this 25-30 centimeter, that it is probably the threshold, the maximum that we can expect to have. We have to keep continuous the system over pressurized, and this will require injection to continuous. This is one point. It will need much smaller volume, so the pumping rate, because just to maintain a situation that has been acquired. We are also trying we are really start thinking and working with other people, or that are, because we are not really expert to this, but the idea should be to see if once, let's say, we have obtained the uplift that we want, let's check to see if we are able in some way to freeze this condition, for example, by injecting together with the water some I don't know, chemicals. I'm not really an expert on this, okay, but some other, not simply water, but something that, for example, can in some way keep the structure of this aquifer expanded without any more needing of continuous pumping. There are a lot of technologies that it is available nowadays, much more, for example, than those that was available 20 years ago when we start thinking and making our computation. So for this is also another point over which this pilot project should be really interesting from this point of view. Let's try to see if we can, at the end, when the maximum elevation should be reached, add to the water some others chemicals or something like that keep the structure expanded. This means that at a certain point also the pump will not be continuous to be in operation, and this is something that should be possible really to test, really to make research, but yeah, but we are scientists, and this is our job, I would say.
Okay, we've got another question. Thank you for the fascinating talk. The insights into environmental effects, specifically on salt marshes, were interesting. However, I'm curious about the impact on the other environmental components, specifically aquifers. What would be the impact on these functions, given that boundary conditions will remain the same? Will continuous pumping be required beyond the initial 10 years? And I think you have already answered this partially to this, but and then what would the implication of a potential crack, and could you highlight the main uncertainty of the model specifically regarding possible catastrophic shifts?
Okay, so let's say about the aquifers, we select, as we say, we select deep aquifers because they are saline aquifer, and so we can really use the seawater, of course properly clean, but we can use really seawater. We show by our computation that the idea is to keep the overpressure well below this maximum threshold in order really to avoid any cracks. So the aquifer, okay, will become more expand, of course, because we will overpressurize the fluid at depth, but without any cracking. And what should cause a crack? A crack should cause if we suppose that at a certain point some cracks should occur, cracks should can cause mainly that in that area cracks is a local effect. Okay, it's not a fault, it's some local effect. This means that in those areas the pressure will drop a bit, or if you want, we need to inject more water to maintain the same pressure. So it's also in the unlikely event that some cracks should open, we can in some way manage this problem in terms of safety of the uplift and the city itself. From the aquifer point of view, we cannot really say that this caused some problem. It is true we have played with a certain model dimension, and because we target the model application over this 10-year simulation. If and for sure, if some steps will be done will move forward, we will have to enlarge the model. The idea is really to play with a larger model in order to put the boundary condition farther away. There are information available, and also within the pilot project, part of this is specifically related to improve the knowledge of the subsurface. So we can also add and increase the knowledge that we have, and also enlarge the model. That for sure.
Okay, thank you. I think we still have some minutes for this webinar, so I had a couple of questions more. The first is about I'm trying to imagine the project once implemented, right?
Yeah.
And I am somehow inspired. My question on what we are observing these days in Venice, that we have the MoSE. Now there is a debate that is growing about what should be the threshold for activation. So the question is why San Marcos should go be flooded because it's below 110 centimeters. Another areas are safe. So when the tide is 1 meter, for example, you already have 10 centimeters or more in San Marco Square, and the water flows freely in San Marco Square because the MoSE is open, it's not closed. So I imagine similar circumstances and similar thinking in the case of the implementation of your program, project, sorry. Looking at the maps you showed, with your project, Murano is safe, Burano is not. So there are important decisions to be taken, I imagine. And so the point is, can you imagine also a perspective of scaling up? Meaning, if the point was, for example, to include also some other more peripheral areas, would you think about another center maybe placed on the bell tower of Burano, another wells around it, or more than 10 kilometers, for example? Thank you.
It's good question too. Yes, for sure. Let's say if we remain let's say we put the wells at these 10 kilometers, okay, as a sort of, let's say, experiment. We can of course enlarge a bit, or to make, let's say, to enlarge a bit the wells only to the north if we want to include also Burano. This is something that I would say can be done in the future, that for sure, as soon as, let's say, it's not really a problem, in the sense that if we want to enlarge a bit the area to cover also some other islands, this is really possible without any issue. I received some similar question from friends that works, for example, on similar issue, I don't know, in Jakarta, in Indonesia, or in New York, and they told me, okay, Pietro, can you apply this for the city of Jakarta? And at that scale, I always say probably no, in the sense that, okay, it's the application to Venice and the surrounding islands can be done because the distances are small. So in some way we are lucky because it's a really well concentrated and not scattered over thousands of square kilometers. Thinking of such an idea for a city or mega city as New York or Jakarta probably is not really possible, because we should start drilling hundreds of wells. Management should be really then more or less impractical to be done. So I think that at the scale of the lagoon, we can really enlarge a bit and decide where we want to keep this area, uplifted area, but anyway, remaining in a dimension that it is comparable to what we show in what we get in this preliminary computation.
Okay, I have another possibly last question, because it's already 1 p.m. Something comes to my mind since I study climate change problems is geoengineering solutions for carbon sequestration. So there are projects, and also in this area, maybe a bit southern towards Ravenna, of using abandoned systems for pumping gas or oil to store CO2 in the deep layer. Of course, I imagine it would take quite long to explain the differences between the two things. But is there also a possibility to consider this sort of win-win solution in which you do not store only water, sort of, let me say, sparkling salt water with CO2?
It's clear. No, the question is very clear, and I have to say that we really also thought on this. We say in Italian, due piccioni con una fava. This was the idea, right? And we make some computation already in the past, and what we obtain is that with CO2, this over the threshold on the overpressure must be lower. in order to avoid leakage of CO2 upward. And then if we substitute water with CO2, we have the maximum uplift that we computed is around 15 to 20 centimeters. So it's more or less, I would say 10 centimeter smaller than what we obtain with seawater. So it is in principle doable, but of course it's, let's say, we will gain less elevation. So this is the drawback.
I see, I see. So I think we are running out of time. It was really an incredibly stimulating webinar, as expected, as I said. So simply grazie. Thank you very much for your webinar. And let's stay in contact in the future and see what happens, what will happen to your project.
Yeah, thank you. Thank you so much.
And bye-bye, everybody.
Okay, bye. Bye to everyone.
Webinar.
Bye-bye.
Bye.